Okay, I stopped the last video without showing you the problem, so I'll show you them here in case you want to look at them. Try to do them. And now we'll continue with section 1.3, which is called the complement of a set. So let's see if they have a picture for that. Okay, so here's, we usually draw a box around like that, and then we put the picture, then we put A. So U is called the universal set. That's like the context. So like, for example, if A is some set of numbers, then maybe the universal set is the set of all numbers. But it doesn't include like animals, or it doesn't include cars, or it doesn't include people, right? This is just the context that we're talking about. So like I said, maybe we're just talking about the set of numbers 1, 2, 3 in here. Maybe the universal set is just the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the universal set though is just the context, but you have to be told what the universal set is, what the context is. Okay, so then if given a universal set and given a set A, we talk about the complement of A, and the complement of A is the set of all the things in the universal set which are not in A. So it's the blue region, and in the notation for that is here, A prime. Some books use A with a little C up there. Either way, it's called the complement. Let's take a look at this. Given a set A, we may want to consider those elements that are not in A. Usually, however, there are elements not in A that are extraneous to the problem being studied. For example, suppose A is the set of all positive integers, and we describe an element x that is not in A. Clearly, if x is a negative integer, then x is not in A. However, if x is a cabbage or a walrus, then x is also not in A, since cabbages and walruses are not positive integers. If we are concerned with the problem about integers, then what we really mean when we describe an element x that is not in A is an integer x that is not in A. Cabbages and walruses are extraneous to the problem. So, as I said, we have to be told what the context is. So the context is not including vegetables or animals. Okay, it's just integers. One way of eliminating extraneous elements is to specify in advance that all elements in the problem under consideration come from some fixed set U called the universal set for the problem. For example, in a problem concerned with integers, we might agree to take the universal set to be the set of all integers. Then if we speak of an element x that is not in A, we must mean an integer x that is not in A, since we have agreed that all elements come from the universal set of integers. Okay, in many problems the universal set is intuitively clear from the nature of the problem and not stated explicitly. For example, in problems concerned with letters of the English alphabet, U would be the set of all letters in the English alphabet. In problems concerned with the set of stocks on the New York Stock Exchange, U would be the set of all stocks on the New York Stock Exchange, and so on. In Figure 1, we described the above ideas using a Venn diagram. The points inside the rectangle form the universal set, so inside the rectangle. Since all the sets under study must have their members in U, they lie inside the rectangle. In particular, if A is the set of points inside the circle, then the shaded region in Figure 1 forms the set of all elements not in A, and that's called the complement of A. If U is the universal set and A is a subset of U, then the set of all elements in U that are not members of A is called the complement of A, and it's denoted by the symbol A prime. Okay? Let A be the set of integers consisting of all positive integers. Find A prime. Since A is a subset of the set of integers, it is natural to take the universal set to be the set of all integers. That's A prime. So A is what? The set of positive integers. So A prime is what? The set of integers that are not positive. That is, A prime is the set of integers consisting of the negative integers and 0. Okay, another example. Let W be the set of all U.S. citizens who filed tax returns listing less than $10,000 taxable income in 1980. Find the complement of W. So it's the set of citizens who filed taxable income in 1980 that were at least $10,000 or more, in other words. Okay, here's a U and a set V. So what is V prime? It's the set of all elements in U that are not in V. So it's 3, 9, and 11. 3, 9, and 11. Okay, here's another example. Let U be the universal set for a given problem. Find U prime. Find the empty set prime. So if U is the universal set, what's the set of all elements that are not that are in U and not in U? So U prime is the empty set. And how about what's the prime of the empty set? It's U. Okay? So we can combine set operations. So we can look at things, a statement with intersections and primes in them, or intersections and 2 primes in them, and so on. So they ask you to find the A prime intersect B intersect C in this. So it ends up something like this. You can check these yourself. These 2 statements are true always. That is, A union B prime equals A prime intersect B prime, and this one also. Okay, so you can check this. These are called DeMorgan's laws, and you can check it by drawing the Venn diagram and showing, do a Venn diagram for this and do a Venn diagram for this, and you'll find that you get the same region. So that means that this is equal to this. Okay? And then you can do the same thing here. Do a Venn diagram for this and do a Venn diagram for this, and you'll see that the regions are the same for this one and this one. That means that this is equal to this. Means equals means true for any sets A and B. Okay? Now what's the relationship between this one and this one? If you look at it, you can see that all they did from here to here was they changed union to intersection and intersection to union. So this union becomes intersection and this intersection becomes union. And so you can go from this one to this one by doing that. Okay, but anyway, this is the first of DeMorgan's laws, and this is the second. Okay, they're separate laws. You're not allowed to change union to intersection and just then pretend that it's the same, but it turns out that it is the same. And you can, and as I said, you can prove both of these statements, 1 and 2. So they do that here. You can look at them. Let's just show that a little bit more clearly. Okay, so you can check that, or you can do it yourself. And then they give an example. Here's A union B prime. That's one of the parts of one of DeMorgan's laws, and supposedly that's equal to, I think, A prime intersect B prime, and it turns out you get the same thing. So they check with a specific U, a specific A, and a specific B, and show that DeMorgan's law is true. But just checking for a specific U, A, and B doesn't mean that it's always true. To show that it's always true, you can do the Venn diagrams, and that will mean that it's always true. This is just an example of that, of one of DeMorgan's laws. Of course, if it's always true, it has to be true for this example as in particular. Okay, properties of the complement. If U is the universal set and A is a subset of U, then A prime prime is equal to A, right? If you take A prime, you get everything. I'm sorry, if you take A prime, you get everything outside of A, and then if you take the prime of that, you go back to A. So the A prime prime is that. Also, A union A prime is everything, right? Do we have the picture? Well, anyway, A union A prime is everything, and A intersect A prime is the empty set. And then they say other commonly used notations for the complement of A are this or this. These all mean the complement of A, in addition to A prime. And also, as I said, some books use AC, with a little C above it. Instead of a prime, they use a little C here. Here's some more exercises. And that's all for sets.